So we've talked about the effect size, so let's move on. Let's talk about the confidence interval. So the confidence interval is an estimate of where we expect the true population mean to fall given our measure of variability and the mean of our sample. So when we collect a sample, we calculate the sample mean as an estimate, a stand-in or a proxy for the population mean. So remember, the whole purpose of sampling is to infer back to the population, and we hope that when we sample that we do so in such a way that it represents the larger population that we wish to infer to. But because the sample is an estimate, it's our best guess of what the population mean is, that because of that, the sample and the population mean are not likely to be the same. And so what we would like to do is create an estimate or an estimated range of where we might expect that population mean to fall. And so that range of our estimate for that population mean has to be at some level of confidence. In other words, a confidence interval. So the data we collected showed that the population performance with the new training is estimated to be 76 based on our sample. However, we already know that our sample mean is not the true population mean of all employees. It's our estimate, it's our best guess. And so what we want to do in this particular scenario is estimate the range of where we would expect the true population mean to be for this new training. So if we were to implement it nationwide to all of our Applebee's employees, where could we expect the true population performance mean to fall with this new training will depend upon that range that we estimate. And of course, when we estimate this range, we want to indicate at what level of chance that this population mean might fall within this particular range, and that's our level of confidence. So to calculate a confidence interval, we need a few things. We need to know our alpha. We also need to know the associated z critical values with that alpha. We need to know our sample mean, and we need to know our standard error. And so there I give you the two formulas. We have an upper bound and a lower bound. So it's a range, and so we need to get a low value and a high value of this range of where we expect that true population mean to fall. Now I've left a couple notes there just to remind me of a couple things I need to talk about. So first of all, confidence intervals are always two-tailed. And so we talked about our hypothesis tests on Thursday, that they can be either one or two-tailed, but our confidence interval will always be two-tailed. And the reason why is that we want to create a range around the sample mean. So if a sample mean is our best guess, it's the estimate for the population mean, then we could be wrong. Our sample mean may be higher than the true population mean, or it may be lower than the true population mean. And so we need to set critical values in both tails of our distribution in both directions. So when we have our sample mean, we're going to create a normal distribution centered at that sample mean. So here is our normal distribution. You'll notice that the properties of this normal distribution are exactly the same as it's been all semester that you've learned. So it's divided up by standard deviations, or what we call z-scores. But now it's centered at the sample mean of a performance appraisal rating of 76, rather than at the population mean of 72. So this distribution represents the performance of those employees with the new training, rather than the performance of employees with the old training. So again, it's now centered at the sample mean, not the population mean. So if we take our distribution and we put in our critical values, so again we use the same alpha that's in our scenario. So we said we had an alpha of 0.05. We said that confidence intervals are always two-tailed, so we need to divide that alpha by 2 and come up with the associated z critical values. And so because it's a two-tailed test with an alpha of 0.05, our z criticals are going to be the same as it was with our hypothesis test. So in this case, negative 1.96 and 1.96. Now it's important to note that if you did a one-tailed hypothesis test, so if our scenario suggested that performance would only increase or only decrease based on previous research, then we would need to calculate new critical values. If our hypothesis test is a one-tailed test and our confidence intervals are always two-tailed tests, then we need to go back and we need to get new critical values for our confidence interval. But in our particular example, we had a two-tailed test hypothesis test, and we have a confidence interval that's always going to use two tails. So in this case, our z critical values remain the same. They did not change. So if you remember from our scenario, when we were calculating our test statistic, that the mean of the sample was 76, and so that is where we will center our confidence interval. So let's go ahead and let's put in those numbers from our scenario to go ahead and get our confidence interval for our Applebee's example. So we'll see here that we had an alpha 0.05, that the associated z critical values for two tails is plus or minus 1.96. Our sample mean is 76 and our standard error is 2.19. So we can go ahead and plug those numbers into our two formulas to get the upper and the lower bound of our range. Now it's important to note here that when we say negative z critical in our formula, in z critical, so for the lower bound we say negative z critical and the upper bound we say z critical, what we're talking about is the positive and negative value of the z critical. Sometimes I'll see students put in the z statistic that they calculated for the hypothesis test. That would be incorrect. We want the critical values. Sometimes also I see students put in the negative z critical, so they end up with a negative and a negative z critical, and they make it a positive z critical, and then their upper and their lower bound is the same number. So just remember that negative z critical is just a negative critical value. For the upper bound, the positive z critical is just a positive z critical value. So if we were to put in the numbers for the lower bound, so m sub lower, we would say it equals negative 1.96 times 2.19 plus 76. The upper bound of our interval would be 1.96 times 2.19 plus 76. And then we can calculate our range for our confidence interval. We end up getting 71.71 from our lower bound and 80.28 for our upper bound. And so what we're saying is that the true population mean for this new training, for performance with this new training, will fall somewhere between 71.71 and 80.29 performance ratings. If we were to write this out, which I will ask you to do, we need to include a few things. The first thing we need to include is the percent chance. Now the percent chance is based on your alpha. So in this particular case, we had an alpha of 0.05. So that was a 5% chance for a type 1 error. So if we take 100%, our entire distribution, subtract our 5% chance for a type 1 error, we get a 95% chance. And so that becomes our level of chance for our confidence interval. So an alpha of 0.05 will be a 95% chance. An alpha of 0.10 would be a 90% chance. An alpha of 0.01 would be a 99% chance. And so we always want to include the level of chance when explaining our confidence interval. So we might say that there is a 95% chance that the true population mean, and we want to say that, we want to say we're looking for that population mean. So there's a 95% chance that the true population mean for Applebee's employees performance for the new training will fall between 71.71 and 80.29 performance appraisal scores. So just like all of our other descriptions that we need to write, we want to include who or what's being measured, in this case Applebee's employees. We want to include what's being measured, we're talking about performance. We want to talk about the group that is based on our sample, so in this case those with the new training. We want to include our percent chance, and we want to include that we're looking for the population mean. So if we were going to write it in APA format, we'll see that in orange at the bottom of the slide. We'll say 95% CI, we'll give a bracket, we'll say 71.71, comma, 80.29, and we'll close the bracket. So essentially what that's saying, that there is a 95% chance that the true population mean for Applebee's employees, their performance for this new training will fall somewhere between those two performance appraisal scores. And so you should also recognize that when we have a confidence interval, and you should include this in your description as well, is that we're talking about the raw scores that we originally collected. So we're talking about performance ratings here. We're not talking about z-statistics. We're not talking about standard deviations. We're talking about performance appraisal scores. So again, our best guess for the true population mean was the average of our sample. That was 76. However, we knew that our sample mean was not going to be the population mean, but the population mean should be around that sample mean, and so we create this range of where we expect that true population mean to fall. It could be as low as 71.71 or as high as 80.29, and that's with a 95% confidence or at a 95% chance. And that's your confidence interval.